Okay, so we are still looking at electrical double layer models. So what we had done in the last class was to look at working out solution for a case where you have a planar surface that is charged, okay, that is in a bath of electrolyte, okay, and we were trying to look at how does the potential vary as a function of separation distance x, and then we found that psi goes as psi naught exponent minus kappa x. Okay, that is what we had derived. That's we took a case of planar surface. So, what we are going to look at today is a case where instead of a planar surface I have a curved surface. Okay, if I have a spherical particle for example, and if that is charged, we will think a little bit about how do we derive an expression for how does the potential fall with distance from the spherical surface, and then we will talk about a parameter that comes out of all the analysis that we have done. Okay, it is what is called as a Debye-Huckel parameter, and finally, we will try and compare. We have looked at capacitor model, which I said is one of the most simple model that people have developed. We will try and compare that with diffuse double layer model, and by that comparison you can actually draw some nice inferences. Okay, so we will discuss a little bit about that. So briefly I had mentioned this yesterday. This is now the linearized Poisson-Boltzmann equation, okay, but in the case where I have a spherical surface that is charged, and I would like to look at the variation of psi with r. Okay, and so to do so we start with the linearized PB equation, and we can do some simple modifications, right. I can, if I substitute for x as r times psi, okay, this is just a simple steps, because we would like to have a differential equation which I can eventually solve, okay, and then get an expression for how does psi vary as a function of r, right. That is what we are after. Okay, so we will do a simple substitution. If you substitute x is equal to r psi, okay, so that is this term here, right. I keep it the same, and I am going to take r square to the right hand side. So therefore I have r square, and this we know is kappa square, right. That is what we defined yesterday, that is kappa square, and you have psi. Okay. So therefore I am going to keep the left hand side same, okay, and the right hand side, instead of r times psi, okay, I am going to replace that with x. Okay, r times psi is going to be x, and I am going to retain 1 r and kappa square, right. That is what we have done. This term, right, d by dr of r square d psi by dr, I can actually write it as d by dr of r square. Instead of psi I can replace it with x by r, right. I can replace that with x by r. Therefore, this become d by dr of r square into 1 minus r, sorry, 1 divided by r into dx by dr. Okay. So, this is basically if you have d by dr of uv, right, it is u into dv by dr plus v, right. So, you are going to use a chain rule, right. That is how this is done, right. Therefore, this becomes d by dr of r square into 1 over r into dx by dr minus x into 1 over r square, right, minus 1 over r square. Therefore, you get the right hand side. Okay, so that is what is written here. Okay, this is what we essentially obtained. Now, because I have r square, I can multiply, I can take the r square inside. Therefore, this becomes multiplied by r square multiplied by r square, right, and this r square gets cancelled. So, I have x here, and this becomes r into dx by dr. Okay, just a simple manipulation. Okay. Therefore, d by dr of r square d psi by dx dr, okay, essentially is d by dr of r times dx by dr minus x. Okay, I can further expand this, right. I can write this as d by dr of, if I so I can write this as dr, again I can use the product rule, right. So, d by dr of r into dx by dr plus r into d square x by dr square minus dx by dr. Dx by dr and dx by dr gets cancelled. Essentially, you are left with r into d square x by dr square. Okay. So, therefore, essentially what we have done is, so therefore, this is the equation that we started off with. Okay. Okay. It ultimately becomes, with this simple manipulation, it becomes r into d square x by dr square is equal to, this is the right hand side that we had, right, r into k kappa square into x. Okay. Because again we had defined x as r times psi. Okay. Therefore, I mean that is what we had defined, right. Therefore, d square x by dr square becomes kappa square into x, because your x, r and r gets cancelled here. Okay. So, essentially I have a simple differential equation now which I can solve. I know that the solution for this particular differential equation is x is a exponent minus kappa r plus b exponent kappa r, right, that is the solution. And therefore, but because I know that x and psi are related, therefore, psi becomes a exponent minus kappa r divided by r plus b exponent kappa r divided by r. Okay. That is the solution of this differential equation, and of course, we would have to solve it, right. I mean, I have to get these constants a and b. For that, I am going to use the boundary conditions. Okay. And the boundary conditions that we have is that psi tends to 0 as x tends to infinity, right. And if you look at this expression, this condition will only be satisfied if b is equal to 0, right. The fact that psi tends to 0 if x tends to infinity, okay, or r tends to infinity, right, is only satisfied if b is equal to 0. Therefore, b is equal to 0. Therefore, the solution becomes psi is equal to a exponent of minus kappa r divided by r. And if I use the other boundary condition, that is at the surface of the spherical particle, for example, if the size of the spherical particle that I am considering is r s, okay, that is the radius of the spherical particle, at r is equal to r s, psi has to be psi naught, okay, where r s is the radius of the spherical particle. Okay. If I substitute for that, then I can get an I can get the constant a out. Therefore, psi goes as psi naught r by capital R s divided by r exponent of minus kappa into r minus capital R s. Okay. That is the solution we get. Okay. So, again like similar to the case of spherical linear for the case of flat surfaces, the potential in the case of spherical surfaces also falls exponentially with distance. Okay. That is all this captures. Okay. The functional form, whether it is a planar surface or the spherical surface, is very much similar. That is also because of the fact that we have considered a linearized version of the model. Okay. So, that is the that is how you, this is the expression that tells you something about the potential distribution around a spherical surface. Again, this is a Debye-Huckel approximation, because we have considered the case of low potential. Okay. That is when we can have a linearized version of the Poisson-Boltzmann equation. Okay. So, that is okay, this is just a comparison. Okay. That is for the planar surfaces. Okay. That is for a curved or spherical surfaces. Okay. Okay. So, yeah, a couple of things to keep in mind when you are looking at these expressions are, these are strictly applicable in low potential cases. That is what we have assumed throughout these derivations. So, that is very important. Okay. And so, this result is a limiting case to which all equations that are more general must reduce to at low potential. That means, if I have a way of deriving a similar expression for how psi varies with distance, okay, for a more general case, what I mean by more general case is, you could have the potential need not be low, okay, if you have a very high potential case, or if you have cases where I have variation both in x, y and z direction, right. So if you have a very general expression like that, and if I take that expression and then put in the condition that look, I have an expression which is a general expression, now I am going to apply the condition there is a low potential. So if you use that, all these equations that you developed should basically give rise to these limiting equations, right. Yeah.
Low potential means the charges, the particles are less amount, or
no, when I say, see, this is okay, let me go back to that. So what do I mean by low potential? Okay, so when we wrote, so I said this was an exponential term here, right. This was actually exponent minus zi e psi by kbt. Okay, I can write this in this form only when zi e psi is less than kbt. Okay, so that's how the low potential was derived, was thought of. And then we said that if I am working with a monovalent, because there was zi here, right. If I assume that I am working with a monovalent ions, zi is going to be 1. Okay, so this limiting, so basically I can estimate a potential, okay, if I know what is the charge on the electron and the thermal energy, right. That potential turns out to be something like this. Okay, and this is a this is a limiting potential below which I can say that the potentials are low potential. Okay, so typically a potential like this, I can say that the particles are reasonably less charged, compared to cases if I have like say 100 millivolts as a potential, surface potential for example, or zeta potential, that would be really highly charged. Okay, whereas if I have potentials which are 20, 25 millivolts or even lower than that, you can take these cases to be low potential cases where I can use this linearized solution of linearized Poisson-Boltzmann equation to really understand the potential variation with separation distance. Okay, and as we are going to do, as we are going to discuss later, how this potential varies with distance is really important. I do not have a solution here. Okay, so yeah, let me just go back. So how this potential varies with separation distance is really important, because that is what is going to determine the electrical double layer repulsion between the particles. Okay, we will discuss a little bit of that in the next class, maybe a few lectures. Okay, so again to recap, so they are strictly applicable for low potential, and this is a limiting case to which all the more general solutions should reduce to when we invoke the condition of low potential case. And so these expressions, okay, so what these expressions also capture is the effect of electrolyte concentration and the valency. Okay, so okay, let me put it this way. So these expressions, they capture the fact that psi varies in a particular way when you have when the concentration of electrolyte in the solution changes, or when the valency of ions in the solution changes, right. Okay, so that means if I have like say okay, let me put it this way. So if I have potential, if this is psi naught, say that the potential varies in this particular way with if I use say 1:1 electrolyte. Okay, now if I use the same electrolyte but I go for a higher concentration. Okay, so this is concentration 1. Okay, say this is again 1:1, the concentration 2, where concentration 2 is greater than concentration 1. Okay, so there is a particular way. Okay, this potential will vary with distance as you change the concentration of the salt, or as you change the valency of the ions that you have put in the solution. Okay, so these in the limiting cases still capture the variation of psi naught with separation distance in a consistent way, which is also captured by more rigorous calculation. The only thing is the magnitude may be slightly off, but the way psi varies with electrolyte concentration and valency is still qualitatively very similar, okay, whether you use a rigorous model or these limiting cases. Okay, that is the point. Is that okay? I mean, yeah. Okay, so the effect of electrolyte concentration and valency in this approximation, okay, are qualitatively consistent with the results of more rigorous calculation. There may be quantitative mismatch because you have invoked the low potential case. However, in terms of the nature of variation, okay, they are qualitatively they are similar to the more rigorous calculations. Okay. Now, in these expressions, right, this kappa square, okay, we had taken it as it turns out during the simplification, kappa square comes out as epsilon square divided by E square divided by epsilon kBt multiplied by summation of I n I infinity z I square. Okay. Let us look at what is the unit of kappa. What do you think is the unit of kappa? I'll go by a simpler way of doing this. You look at this expression, right? Psi is equal to psi naught exponent minus kappa x. X will have units of length, therefore kappa should have units of length inverse, right? So the parameter kappa should have a unit of meter inverse, right? Or K inverse should have a length unit of length. Okay. This kappa inverse is what is called as a Debye-Huckel parameter. That is because this comes out when you are looking at Debye-Huckel approximation, right, the low potential case. That is why it is called a Debye-Huckel parameter, and people often refer to K inverse as the thickness of the double layer. Okay. Thickness of the double layer. People also call this parameter as Debye. So, K inverse, which has units of length, is called as Debye length, and K, which has units of meter inverse, is called inverse Debye length and stuff like that. Okay. So, but these are the names that people use interchangeably depending upon different textbook and different okay. And so, like we mentioned that we always kind of compare the interaction potential, right, u or phi, we always try and compare and they say something about what is the potential with respect to kBt, right. Okay. I mentioned that whenever you do any interaction potential calculation, is always a good idea to scale your interactions with the thermal energy, because that will give you a kind of a magnitude which you can easily connect to. Similarly, all distances, okay, all distances within the double layer are judged with respect to the double layer thickness. Okay. So, when you are working with electrical double layer interactions in charge dispersions, okay, you will always ask a question as to what is the size of the particle compared to K inverse, okay, what is the distance between the particles compared to K inverse. Okay. So, therefore, okay, so all the distances within the double layer and all the interactions, the range of interactions that you talk about in electrical double layer interactions, you can people always try they are judged with respect to the distance of the thickness of this double layer. Okay. Now, this Ni infinity is the concentration of ions, right, that is the number of ions per unit volume, right, that is what we had mentioned. You can express, you can actually kind of just rearrange this expression and then express k square in terms of more measurable quantity. So, I can this Ni infinity, which is the concentration of ions in the solution, right, you can express that in terms of the molarity of the salt that is added, right, because molarity will have units of moles per liter, and because I want to convert that into moles per meter cube, I multiplied by 1000, okay, and because I have moles, I would like to convert that into the number of, okay, I would like to convert that into number of ions, therefore I am multiplying by Avogadro number, therefore kappa square becomes E square divided by epsilon kBt, okay. I can replace Ni infinity with 1000 Mi Na and Zi square, okay, and Na being a constant I can just take it out, and 1000 also I can take it out, therefore kappa becomes 1000 E square Na divided by epsilon kBt summation of I Mi Zi square to the power half. Okay, so I have missed out. So that's kappa, right. So far we are writing kappa square. Okay, so the kappa essentially is the entire thing to the power half. Okay, so these are some typical values. What is this? Is a table that I have taken from the book. This is the molarity of the salt. Okay, different salt concentration, 0.001 molar, okay, 0.01 molar, 0.1 molar, and this is a Z is to Z electrolyte. This is for symmetric electrolyte, okay, 1:1, 2:2, 3:3, right. These are all symmetric electrolytes, okay. The next few columns are for asymmetric electrolyte, okay. That is again Z is to Z, but you could have 1:2 or 2:1 electrolyte, or 3:1 or 1:3, okay. These are asymmetric electrolyte, right. And so these are kappa values, okay, that is the Debye-Huckel parameter, and this is kappa inverse, okay, that is the inverse, or the AA thickness, right, which has units of meter, right. And what is interesting to note is that all these numbers, okay, if you look at all these numbers, they are again of the order of nanometers, right, they are of the order of nanometer. That is again important to keep in mind, right, whenever you do any calculation where you have been asked to calculate kappa inverse, okay, if you get values which are microns or really large, that means there is something wrong with your calculation, because kappa inverse values are supposed to be, okay, in the nanometer size range, okay. And so if I look at these numbers, right, if I look at these numbers, one comment that I can make is that the thickness of the double layer, okay, is about the same magnitude as the prediction based on the capacitor model, right. If you remember the calculation that we made, if we took a simple case and we showed that the thickness delta, right, the delta, that is the separation distance between the parallel plates of the capacitor, we said it was coming to be something like 4.4 nanometer or something like that, right. Okay. So if you look up these numbers, okay, the thickness of the double layer is of the same magnitude as that predicted by the capacitor model. However, the diffuse model captures the dependence of AA thickness on the concentration and the valency of the ions, okay, which was not there for the capacitor model, right. For the capacitor model, delta was fixed by the potential drop, okay, it was fixed by the potential drop, it was fixed by the dielectric constant of the medium, it was fixed by the sigma star, which is the surface charge density, right, because we had something like delta psi by del psi by delta was going as sigma star divided by epsilon naught, right, epsilon r epsilon naught. I think that was the expression that we had, right. So this delta is fixed by the potential drop, the surface charge density, and the permittivity constant of the medium that you have between the plates, right. However, so the capacitor model did not capture, okay, the variation of delta with the concentration and the valency of ions in the solution. However, the diffuse double layer model does capture that. That is one of the difference. So, the other inference that you can draw, if you go back and look at this expression, is that k, okay, the kappa, okay, it varies as m power half, and it varies as is proportional to z, or kappa inverse is inversely proportional to m, the concentration of the electrolyte to the power half, or kappa inverse is inversely proportional to z. Okay. So, that again is kind of okay. So, if you look at these values, right. So, this is a case where I have like if you look at I mean some typical numbers are given. Okay. So, this statement we already made, the thickness of the double layer, that is kappa inverse, okay, it varies inversely with z, that comes straight away from the expression that you had, okay, and it varies inversely with m power half. Again I can make this statement only for z is to z electrolyte. Okay. So, that is okay again here, right, it goes as z kappa inverse goes as 1 over z and m power half minus half, but however for the non-symmetric electrolyte it is a little bit more complicated. Okay. And the double layer thickness equals to about 1, right, if you look at this expression. So, I take 0.01 molar, okay, and for 3:3 electrolyte, okay, the double layer thickness is about 1 nanometer. Okay. Okay. However, if I take 0.001 molar electrolyte, and if it is 1:1 electrolyte, the double layer thickness is about 10 nanometer. Okay. So, I mean you can get these numbers and think a little bit about how does so essentially what I am trying to tell is that if I compare, okay, so let us think about so 3 cases, okay, 0.001, 0.01 and 0.1. Let us stick to 1:1 electrolyte. Okay, I am keeping the same type of electrolyte 1:1, but however we are changing the concentration, right. Therefore, in one case the double layer thickness is about 10 nanometer, and I increase the salt concentration, the double layer thickness becomes 3 nanometer. Okay. I increase the concentration further, the double layer thickness becomes about 1 nanometer, right, about this is about 1, right, 9.61 10 power minus 10 is 0.9, right. So, therefore, if I keep the type of electrolyte same, if I increase the concentration, okay, from 0.01 to 0.01 to 0.1, the double layer thickness goes from about 10 to about 3 to 1. Okay. It was 10 nanometer here, there is 3 nanometers there, and it is about 1 nanometer here. Okay. So, basically this basically the formalism that we have done, right, the Debye-Huckel approximation essentially captures how does both the potential vary with distance, okay, and how does it vary with the electrolyte concentration, okay, how does it vary with the type of electrolyte that you have used. Okay. These are the so this is again just a plot, okay, whatever I mentioned in the previous last few seconds. So, similar so what is plotted is a scaled potential. So, I can divide this by psi naught, right, I can get this, that is what is on the y axis. X axis is your separation distance, okay, that is for 1:1 electrolyte, okay, and all that has been done is the salt concentration is systematically increased. Okay. So, that means you get a more steeper, okay, more steeper drop in the potential with separation distance when you have a higher salt concentration, and the fall becomes more gradual if you have low salt concentration. So, in this case the type of electrolyte is fixed and the concentration is changed. However, if I fix the concentration of the electrolyte and change the type of electrolyte 1:1, 2:2, 3:3, again symmetric electrolyte, you will again see that the potential decrease becomes more and more gradual if you change the electrolyte from 3:3 to 2:2 to 1:1. Okay. So, therefore, these potential, the plot of how the potential varies, they drop off more rapidly for higher concentration or higher values of higher valencies of the electrolyte. Okay. What do you think is the implication of this? What do you think is the implication of the fact that the potential drops off more gradually or more rapidly? What consequence do you think this has on the electrical double layer interactions? Okay. Think a little bit about this question. So, I will come back and we will come back and make a point. Okay.